Okay, so let me give you guys a slightly different context. So this is going to be a thing called a scalar line integral, and this is basically just an exercise in Riemann integration. So the first thing I'm going to do here is I'm going to write some crap down, and then we'll go on a little field trip. Okay? So here's my idea. I would like to build a big ass fence.
Big or big?
Yes. I don't know. So this is an ill-defined problem, right? But the idea is basically I have some kind of a handkerchiefy thing, right? Always.
Is that your property? This is deck.
This is not the deck. Okay, this is worse than the deck. Actually, you could have used this. This could be used on the patio, but we'll pretend it's not on the patio today. So here's my issue. I have in the XY plane some kind of path here. Like from here to over here that goes like this. That's going to be really annoying to draw. Okay, so that's some kind of R of t, right? Thing two-dimensional. So that's like an x of t comma y of t, right? Okay, now the heights of my fence are not necessarily consistent, right? Because some places I would like my fence to be taller than others. Why? Because some places I have nosy neighbors and other places I don't, right? So where the neighbors are nosy, I would like the fence to get taller. And where the neighbors are not nosy, I would like the fence to get lower, right? So above this thing, I'm kind of using this surface, right, to describe my nosiness of my neighbors. And this is going to be my fence that I have to build.
There's also,
if
you wanted the same top height, just your building on top.
Yeah, so if I wanted the same top height, right, I would just have a plane here instead of this kind of wibbledy surface. One thing you could think about this wibbledy surface is you could do the opposite of this, right, where you build a plane, right, and you're going down to the ground. So you want a fence that's at a constant elevation, but of course the ground changes height. That's just this picture flipped over, right?
Yep, that's what we had to face with my dad.
Yeah. You guys cool with that? So that totally happens. You could do that as well. That would be like the current geopolitical version of that would be if Donald Trump declared the border wall will all be at an elevation of 6,000 feet to stop drones from flying over it.
Oh, nice.
Right? Like, so the whole way it's going to be at 6,000 feet. It's going to be 6,000 feet tall in San Diego, right? But then up in the mountains in like Arizona, it's only going to be, a couple hundred feet tall. See this? So that's this picture flipped over, right? So the way I figure out how much material I'm going to use for this fence, right, is I'm going to kind of push this blue path up, and that's going to make some kind of bendy funkiness, right? You guys all with this? And then, of course, I want to think about how much material does this take. So I'm looking basically for the surface area of this little kind of wibbledy slice that's between the pink curve and the blue curve, right? You guys see that? Kind of, sort of, maybe?
Yep.
Okay, so
I see it.
I need a way to figure that out. So what do? What do you start with?
Well,
Anytime you want to start with integrating a new thing,
Start with rectangles.
yeah, find some rectangles, find some little changes, write down a formula that's an approximation, and then limit everything, right?
yeah.
Okay, so we're going to do that. We're going to chunk this up into some pieces. So I'm going to just instead of building a nice curvy fence, I'll just build it out of slats first, right? Is it going to be exactly right? Nah. Is it going to be close? Sure. So here's my slats, right? So like there's a rectangle, here's a rectangle. This one's going to be weird because that, of course, is where the base of my slat sits. You guys see that? And then like this one's going to be funky. You see like these guys are pretty close. Those guys are kind of taking a shortcut across the curve, right? So these are also not quite on point. Those are going to be like slight shortcuts across the curve. You guys all see this? Okay, so let me kind of dot, dot, dot that and continue drawing those. And then I want to pull one of them out. So if I pull one out, and I'm just pulling the base, right? So this is just going to be a picture right there. You guys with me on that? Okay, so I've got a base, right? So this is my R of t curve, right? In between there. And then, where's my slat?
Just like bridging those 2 points, right?
Yeah, the slat's going to go in between these. Is all with that? Oh, my slat's pink. I have a pink marker. You all see this? Okay, so let me just write what's the area of a slat going to be?
This is between the sheet and the product.
Basically an integral.
Times the width.
Okay, right. It's just the height times the width. Because it's kind of a square, basically. So I need to give my kind of wibbledy sheet a name. I'm going to call that f of x and y, right? Because what else are you going to call it?
Yeah.
You guys cool with that? Okay, so my area of my slat's going to be like f of, ooh, huh. It's not f of x and y, right? Why isn't it just f of x and y?
The height?
That would just be the sheet. That would be the distance between the sheet and the base.
That should be x minus y.
Yeah, so here I'm thinking, right, this is the xy plane, right? So that's z is 0. So this distance is kind of the distance I'm talking about.
Oh, so it's x, z?
That would be f of x and y, except that I'm doing that at, where am I evaluating f of x and y? Yeah, I'm going to evaluate at one of the ends of this thing or someplace in the middle, right?
Yeah.
But what I'm really trying to get at is that has to be some special x value that's in there, right? And some special y value that's in there. Oh, and these don't really need to be different, right? Because I'm just chunking this thing along the fence posts, right? You guys see that?
Yep.
So for this guy, you could really think like the left end of the slat or the right end of the slat or someplace in the middle. You guys cool with that?
Okay.
Okay, so that's kind of the height. And then what's the width?
It's just,
Yeah, kind of the distance between the 2 points, right?
yep. So is that,
But that's
Like
the,
x, y, y.
there's like 2 points. It's
Yeah, it's like this, right?
Oh, it's a distance vector. Is it a distance vector?
delta of t.
It's like x's and y's and shit. I think that's the change in y there, right? That's the change in x there. You guys with me on this? So what's this guy?
The change of x squared plus the change of y squared?
The square root of the change in x squared plus the change in y squared? Which is a good approximation of the arc length, right? You guys with me? Yeah. So as this shrinks down, right, that's going to go to the arc length here, which you might remember is not calculated this way. You might remember arc length is 1 plus f prime of x squared, quantity square root. There's a similar way to formulate this. You'll get the same thing out of this guy.
We don't cover this at all?
What's that?
Don't we cover this at all? Are we?
No, you should have covered in Calc 2.
Really?
Yep.
You don't do the integral of that?
Should we in Calc 2? We're going to do some stuff that's going to give us arc lengths, but this is where we get that from here. Because our functions are a little bit different than the Calc 1 functions. We have actually a stronger tool here, because I'm doing this with respect to time, right? So I've still kind of jacked this up. I'm just thinking still. And the thing I'm missing is that, like, this is all in terms of x and y, right? But I don't really have x's and y's, right? I have like a curve with t's. You guys see that?
Yeah.
So I need like some t's somewhere. Where do you get the t's from? They should be in here. Like the category of object that I get at the end here should look something like you should integrate some crap dt. Right?
Couldn't you write delta x and delta y in terms of t? Some delta t.
Yeah, I think we probably should, right? You guys all with that?
Okay, yeah.
Okay, so let me think here. So I've got this curve r of t, right? Okay, let me pick some stuff. So I'm going to say this end happens at t is a, right? Just to slim things down. So once I've got that happens at t is a, where are these guys? I'm just going to do a left-hand endpoint just to make things easy.
X sub a, y sub a?
Close. X of a, right? You have a function r of t that gives you x's and y's. So really, you could just do, instead of x of t and y of t, or x of a and y of a, you could do here r of that a value, right? Really, you might think here instead, you might do f of r of t star, right? But that's just some special time in this interval that you pick to evaluate at. You guys all good with this? Kind of, sort of?
So far?
Okay. All right, now I need to do that same conversion with my delta x's and delta y's. Right?
Yeah.
Okay.
So wait, that's x of b minus a, or trying to figure that out.
Yeah, I'm trying to approximate a difference, right? You guys see that? So like if this is t is a and this is t is b, right? Then this change in y is like
Y sub b minus y sub a.
y of b minus y sub a, right? And this guy here is like x of b minus x of a.
Yep.
You guys noticing this feels a little bit like a rise and a run?
Yep.
Okay, so hang on. That feels like I'm taking the b thing and subtracting the a thing, right? Okay, so wouldn't that be r of b minus r of a? Wait, I fucked up. That's the wrong category. What is that thing categorically? What's r of b minus r of a categorically?
A vector.
That's a vector, right? What are these?
Lights. Or real numbers.
Yeah, those are scalars, right? Those are like those are a side length of a triangle, right? But what am I doing with those things? What did I do with those guys? Yeah, I square summed them, right? I squared this one and added it to that one squared anyway. How do I get that out of this vector?
Let's see.
Difference
Oh.
of y and difference of x. Or the x and t,
Yes. This guy here, right?
Oh, how'd you get
This
that?
is
Oh, because R is.
This is a vector that's y, or sorry, it's x of b minus x of a, comma, y of b minus y of a. Right? So, what reason in the world would you have to square sum those and, yeah, that looks like a magnitude, right? You guys see that?
Yeah.
So this is actually my slat, right? Pretty quickly I'm running into the idea of that feels like I've got f of r of a times the magnitude of r of b minus r of a. You guys with me on that? But wait, what does that feel like?
It's still the width of the slat, right?
Yeah, so this thing's still the width of the slat. This piece I'm pretty comfortable with, right? Like, really, maybe I should put a t star in here just to be totally legit. So that's some special t in the interval I'm talking about, right? And then there's this business going on. But what the heck is that thing? That's like a change in what?
Change of distance. It's a magnitude in the end.
Yeah, so this is a magnitude, right? This is the magnitude of the change in
R?
r, right? You guys all good with that?
Should there be a hat on top of R?
Yeah. Thank you. Okay. That feels like a derivative thing to me. Doesn't that feel like a derivative to you guys?
Yes.
So what are you differentiating? What are you thinking of this thing?
You're differentiating R.
Like I'm trying to find the magnitude of the change of r, right?
Yep. And we're trying to get to where the change of R approaches 0.
So what's r prime? Like what should r prime be? Should be the, how would you approximate a derivative? Like what's y prime? Yes, slope of tangent line, right? So it's the change in the y's divided by the change in the x's. So this is the, right, r prime of t should be basically the change in the r's divided by the change in the t's, right? You guys with me?
Okay.
Okay, so the magnitude of r prime, so the magnitude of the change in r, right, should be,
Yes. Function, the formula.
so I've got f of r of t star, right?
Yep.
That's my height. I'm good with that. And then here I have times, and here I want to put in a magnitude of the change of r, right? Okay, so let me solve this thing for change in r. So what's change in r approximately?
R prime T times change in T?
Yeah, it should be r prime of t times delta t, right? You guys all with me on that?
Yep.
Okay, so that's multiplying by, so what's the magnitude of that thing?
Gosh. I'm trying to think. Magnitude.
Magnitude of RT times the change in
So are we supposed to do the magnitude?
R
separately?
delta.
Oh yeah.
So I want you to stick a change in t here. What goes here to approximate that thing?
R change of T. Or R prime of T.
That should be a magnitude of r prime of t. So I pulled a little bit fast and loose here, right? What did I do that was a little bit fast and loose?
A log almost like about equal to.
Yeah, there's an about equals to here, right? And I took a magnitude of both sides, and I didn't apply it to the delta t. You guys all with me on that?
Yep.
Okay, so I cheated just a tiny little bit, but don't sweat it. Okay. So what was this thing? Yeah, that's why I'm getting away with the approximation, because it's an approximation anyway, right? I'm already approximating once. We may as well approximate a couple times, and we'll let the mathematicians worry about whether or not this thing is a valid approximation.
Question: do we use that same given t? No, we don't. Never mind. I was gonna say, do we use it for there and there?
Oh yeah, we should.
Oh, cool.
Because it's the same one.
Right? Because this thing should be a scalar in the end, right?
Yep.
So we better be evaluating that r prime of t at some t I know about. That t should be just my special t that's in the interval. You guys cool with this? I kind of built this at A, but it doesn't matter. You can pick this any place in there. You guys cool? So this is the area of one slat. Then what am I going to do with all of these? Like, what's the surface area of your fence?
Even together.
So this is area of one slat, given by approximately that, anyway. So the area of all of the slats is going to be
Then add
Sum
together.
of all of them.
the sum of all of them, right? So you'd sum up f of r of t stars times the magnitude of r prime of t stars times the change in t. All good with us?
Yep.
Okay. And then, well, you'd really do this sum, right? From t as beginning to t as end. Right? I'm putting t limits on that sum, but I'm totally lying, right? That's not actually how this works. What do you do?
Into one necessary number of
Yeah, usually you take a limit as the number of chunks goes to 0, right? Or goes to infinity, right? So really this should be summing over the number of chunks, right? Starting at the t as beginning and ending at the t as end. You guys cool with that? Okay, so my next thing though is to just hit this sucker with a limit anyway, so it doesn't really matter what I'm summing over. So what am I going to get here? Once you hit that thing with a limit, what do you got?
integral.
Yeah, you got an integral, right? And it's going to be the integral from the beginning of the t's to the end of the t's. This a and b are playing a different role now. That was a bad idea.
C and D.
Let's do t0 to tn. Right? And then what are we going to be integrating? This stuff. So there's going to be f of r of t times the magnitude of r prime of t dt. Perfect.
Did you mean to leave the little asterisk off the T that time?
Yes.
Oh.
Yeah, these are regular t's now. Why?
Evaluating for all values, so it's going to be specific.
Perfect. Because I already sent this limit of the number of chunks to infinity, right? So this is really chunking over every single t. Well, kind of. It's all good with that? Okay. And what was the interpretation of this thing? So this is the surface area
Oh, surface area of the fence.
of a fence with height What was your height function?
F of x, y.
F of x and y
Traced by.
over the curve. What was your curve?
RT.
That was r of t. Oops. 4 t's from t0 to tm is that. Cool.
That'd just be one side of the fence. Uh-oh.
That's an interesting question.
Yeah.
This fence is how thick?
Oh, it's,
Infinitesimally thin, right? Because it's the area over a curve, right? So how much volume does this fence contain? None. So I don't know whether if you painted one side, you would automatically be painting the other, right? There's no volume, so there's not actually anything to stick to anyway, right?
They're painting air.
So if you were doing this absolutely right, your fence would have a little thickness to it, right? And then you would have two curves, and they would be slightly different. So in my mind at least, this is the amount of paint it would take to paint one side of that thing.
Yeah.
And you can worry about whether the material you're making it out of bleeds through or not. Just remember, you're not allowed to have any volume total.
I feel like you need six. You need to have six sides to it. Or it's just like a giant rectangle.
Yeah, he's saying it's basically a rectangle, right? With a kind of a one bent side or two bent sides. Like it's got a top and it's got a bottom and it's got a left end and a right end and then it's got two sides. So yeah, if you built one of these, right, out of concrete, it's going to have six sides. One of them is going to be buried in the dirt. You probably don't need to paint that one,
yeah.
right? But yeah, to paint it, you'd want to maybe double this number. And then think about painting the top and the ends. Cool. Paint will be a not inconsequential cost of the border wall, just so we're clear. Okay, cool. Questions, deals? You guys want to see this in the other room? Okay, so let's take a little field trip.